My name is Rachad, and I lead Android's media framework. Media is an integral part of our life, bringing us together, enabling us to share emotions through music, pictures, and video. Today, we'll discuss how to create these experiences and share them with Android. First, Glenn and Andy from the media team will start with a little story on how to build great audio experiences with Android. Then Lajos and Ollie will continue with great video experiences. And finally, Eddy will introduce us to a very compelling way of building a camera application. Now, please welcome Glenn and Andy for audio.
Hi, all you audio files, video files, and camera files. I'm Glenn Kasten from Android Audio, and my focus is on performance. So given performance, I love integers in audio. Integers are simple, fast, and reliable. You just can't go wrong with integers. In fact, some of my best friends are integers. I'd like you to meet two of my favorite buddies, Min and Max. When it comes to audio, integers are ideal. Fix point 2. 16-bit PCM is where it's at. I just wish it didn't clip. That's why in Android, the entire data pipeline is almost all 16-bit PCM.
Wait a minute, Glenn. That's so 1980s. 16-bit PCM was fine for the days of CDs. But come on, it's 2014. In L Developer Preview, we're introducing floating point audio, starting with the audio track data. We've already updated part of the pipeline, and now we're plumbing out the rest. There'll be significant benefits when the entire pipeline is converted.
But why floating point? That's so inefficient.
Floating point can be just as fast as integers on modern processors, especially with SIMD and out-of-order execution. Floating point improves quality and helps with the clipping too. Check out our I/O bytes, Will It Float, to learn more.
Will it float?
Don't worry, the audio endpoints are still integer.
Oh, whew. And the endpoints can't have more than 16 bits. Woohoo. Now, about that resampler box. Andy, you're not changing that, I hope. Don't mess with my linear interpolator, the fastest resampler in the West.
Glenn, that's so old school. In L Developer Preview, we've worked to improve our resamplers. Better quality through reduced aliasing. Check out the spectrogram of a sine sweep. Before on the top shows aliasing and harmonics, and after on the bottom is clear. We've also improved to twice the speed. So we also dynamically compute our resampling filters to adjust for your sampling ratios.
It's quicker. There we go. OK.
This is all built into the framework. So you can mix, play, and record at different sample rates with great quality. But don't use resamplers if you don't need to, because it consumes CPU and adds to latency.
Latency? Did somebody say latency? That is my favorite topic. I love latency. In fact, here comes one of my favorite developers.
What do you mean you love latency?
Oh, I mean, I love reducing latency. Sorry about that. Anyway, I'd like you to meet Christian House from StarMaker Interactive, and I'm just going to let him tell his story.
So StarMaker is a global talent discovery and enablement network. We make singing games for your mobile device and a platform for you to share your talent with the world. Our goal is to make singing fun again for everyone and finding great talent amongst our user base. But for me, it's also personal. I'm a percussionist, a professionally trained musician, and an educator. And I want to bring the on-stage experience to people who wouldn't normally have that opportunity.
When we first met, you didn't seem too happy with Android Audio. What was the problem, Christian?
Well, part of the experience of being on stage is to hear yourself singing, to be a part of the music, inside that music. Anything that takes away from that just ruins the experience, and I couldn't get that feeling on Android.
Can you show us what you mean?
Here, let me see. Can you hear me now? Can you hear me now?
What? Is that delay from Android?
Yes, that's exactly what we're talking about. It's like singing to yourself across the Grand Canyon. Hearing a delay while you're singing just takes you out of the experience.
But come on, Christian, I heard a couple of seconds of latency. That's ridiculous. That's crazy. If you do a Google search for Android audio, this is number 5, I believe, or 4. There have been some wild rumors out there. Yes, the latency has been high, but not this high.
Yeah. So, folks, that demo was a bit of an exaggeration just for the explanation. But you get the point. The latency is annoying. So I'm going to do a quick demo of what our app is actually like right now. I'm going to shut off my mic.
Some days are long, but I get through it by singing a song. When I let it out, I know that nothing can go wrong.
So, Christian, cut. Hold on a second. Okay, the instrumentals were great, but I'm sorry, I didn't even hear you at all. What's up?
Well, that's the point. We had to disable the real-time feedback because of the latency. Users complained because our most important feature is missing from the app.
Well, it seems like kind of a nice app. I mean, it's almost fun.
Yeah, but we're missing the U in the performance.
I'll say. So how bad was the round-trip latency, or rather, is the round-trip latency?
Well, it's not the 12 seconds that we saw earlier. It's not 2 seconds, but it is noticeable. We've measured 200 milliseconds or more. Enough that we ignored Android completely until our users clamored loudly enough. When we finally implemented the app, we had to disable this real-time monitoring of the user vocals. We've tried to account for the latency and still make a good quality recording for the user to share, but we still had trouble with that too.
Hey, Christian, we can figure this out. Show us how it works inside.
All right. So our current app is still using the Java-based solution. We have 2 MP3 audio files, the instrumental and the guide vocal tracks. We decode and mix those files to play on the headphones. Then we record the microphone input of the user singing, pass it through an audio processing library for pitch detection and pitch correction. As the user is singing, we also mix the instrumental track with the processed microphone stream and encode that into an AAC file for the user to listen to and then later share. What we really want to do is have this all happen fast enough that that processed microphone input could be mixed in with the headphones for you to hear it in real time. That's also going to improve our scoring algorithm and have a more accurate timing of the pitch data.
So at last year's, I'm sorry, hold on a second, let me go back to that. Okay. Oh, well. This clicker is wild. Okay, at last year's I.O., Rafe Levine and I presented reduced audio output latency. Did you even try those techniques?
Well, no, we never did. We read the blog post and saw it probably wasn't ready yet. The other thing is last year's talk was all about output latency. And what was important for our app is the input latency. We need to get that audio moving through the pipeline just so much faster.
So I hear you, Christian, and I hear all of you developers, too. No, I don't love mic latency. I've actually been working on this, and we're going to share our results with you today.
Right. So Glenn has shared his progress with me, and I want to show you what we've been doing with it. We've tried out the new reduced latency APIs in the L developer preview. I'm going to shut off my lapel mic again, and this time you'll hear me actually sing through the app.
Some days are long, but I get
through it by singing a song. When I let it out, I know that nothing can go wrong.
Hey, Christian,
I'm gonna be a star.
I can hear you. sounds great. And how's the latency?
It's dramatically improved. It's finally good enough that with the changes we've done together, I can turn on that real-time audio monitoring.
And did you have to change anything in your app to do this?
Well, it's never that simple. Of course, we had to make a few changes. We followed last year's recommendations and re-implemented our entire pipeline in the Open SL ES APIs, so a full C re-implementation. But it actually simplified our audio pipeline significantly. There's fewer steps now and less places for the synchronization to get off, so our recording's going to be better, and you're going to hear the voice in real time.
And did you run into any problems when you re-implemented?
Well, there were a few challenges along the way. I'm going to tell you about a couple of them. We do a significant amount of digital signal processing with our pitch detection and pitch correction. The CPU load of this can be kind of bursty, which is really awkward with the smaller buffer sizes. Also, we had to implement a resampler because the different hardware devices expect different things. I really wish we had that resampler that Andy was just talking about. And we don't actually yet have this new pipeline in our app proper.
Wow, those are pretty hard problems.
Yes, but they were all solvable. And you know what? The user doesn't really care. Everything that we're trying to do is get the user inside the performance. Our users just want to connect with the artists and to be a part of the song.
Thanks, Christian. Professional musicians and recording engineers expect latency less than 10 milliseconds. We're not there yet. But we have made progress in the platform, and it will enable new applications that are currently not possible. There are a lot of difficult hardware and system integration issues that we need to work through so that we can scale this up to the entire ecosystem. I want to thank all of our partners who have contributed. In particular, Christian Howes from StarMaker Interactive.
Thank you, Glenn.
And I'm hoping she's in the audience. Amanda Chowdhury from Smule has also given us very valuable feedback. So we've just seen several improvements in Android Audio: a higher quality floating point pipeline, new resamplers, and my favorite, reduced round-trip latency. So the big question is, what do we do with all this? We've seen one example of what we can do in terms of singing. I personally am really excited about real-time voice processing, including ordinary speech processing. And another pet favorite of mine is augmented reality. But the big question is, what do you want, Andy?
I'm into audio signal processing, and I really want the improved audio quality.
And how about all of you? What do you want to do? So thank you all for coming. We're going to be available after this session for Q&A, Christian, myself, and Andy, to talk about any questions you have about Android Audio, in particular the problem areas that came up during Christian's demo. Please check out the links above, and be sure to watch our I/O Bytes videos.
And now we hand off to Lajos from Android Video.
Thank you. It's very flaky.
All right.
Be very careful. It's a lot easier to use this. Yeah.
All right. So let's talk about video. First, I want you to ponder this question. If a picture is worth 1,000 words, what is a video worth? Hopefully more than 1,000, maybe 24,000 a second. So why is video so hot? Perhaps this clip for our Nexus 5 campaign can shed light to that.
Way up above, I looked around. For you I was where you were. And now I see.
So video is hot because it's the next best thing to being in the moment, to being with the people that you love, and to satisfy our desire to see. People have been hungry for rich, multi-sensory, multimedia experiences from the beginning. They want to capture and share memories, they want to create, and they want to communicate. In fact, video has been around for nearly 140 years. A Huffington Post editorial actually asked a very similar question about the worth of the video, and concluded that in today's world of social media, a video may be worth more than ever before. And Android is positioned perfectly to take advantage of that. Android has both high and low-level interfaces that enable you to create great multimedia experiences. The high-level interfaces like Media Player, Media Recorder work by themselves. And the low-level ones, Media Codec and its friends, they work as a team. For some applications, the high-level interfaces are enough. Plus, they are supporting the widest range of devices. For others, applications that want to have the best multimedia experience, they use both interfaces. They take advantage of the low-level APIs on newer devices to provide a polished, fine-tuned behavior. And they provide fallback behavior on older devices using the high-level interfaces. And then there are apps that require the low-level interfaces for their operations, such as media editing or some kind of creative applications. And these are not enabled by the high-level API. So there are really no wrong answers of which APIs to use. Today, video is everywhere. In the developed world, basically, you can take video for granted. What increases is the quality bar. So I want you to see how, we're going to go through a few use cases to see how Android can help you aim higher. So one of my favorite pastimes is watching movies, and probably for many others. Video playback has been a standard feature of Android since the beginning, and we continue to make improvements. Bandwidth remains a constant battle on mobile devices. So with the L Developer Preview, we are supporting the best codecs, such as VP9 and HEVC. And these give you higher resolutions for the same bandwidth. In order to take advantage of the available bandwidth, KitKat introduced support for adaptive playback, where you can seamlessly change the video resolution during playback. And in the L Developer Preview, we have dramatically improved the scheduling of video playback, which results in less jitter, smoother pans, and less interference from system events. So here's Ollie to tell you about YouTube and Play Movies and how they are taking advantage of the media APIs.
Hello, so my name is Oliver Woodman. I work on the Play Movies and YouTube application teams, and I'm specifically focused on video playback. So it can be a bit of a challenge on Android, so I want to just tell you a little bit about how we're using these APIs internally at Google in our own applications, and about some of the results that we're able to achieve. So when we talk about high-level and low-level APIs, as Lajos mentioned, when we're talking about high-level APIs, for video playback, we're really interested in Media Player. So it's kind of self-contained. It does everything for you. And both Play Movies and YouTube use Media Player on devices that don't have the newer low-level APIs. So we effectively just have a kind of thin shim which wraps Media Player. And effectively, Media Player does everything for us. But on newer devices, we have these low-level APIs. So we're really interested in Media Extractor, which does networking and buffering and sample extraction of media. Media Codec, which will take these samples and decode them. Audio Track, which will play decoded audio out of speakers. And then Media DRM as well, which will handle encrypted playbacks. So where these APIs are available, we've actually decided to take a different approach. And we've developed an application-level media player called Exo Player, which is predominantly written in Java and calls through to these low-level APIs. So we pull up the player logic, and actually for Play Movies and for YouTube, we actually also pull up the networking, buffering, and extraction components and re-implement them at the application layer. So there are a number of reasons why this is a good idea, and you should think about doing this too. Firstly, it just gives you a lot more control. So previously, all this logic, which was part of the framework, is now part of your app. You can easily update it. You can easily customize it to suit your exact use case. And you can easily implement features that Media Player just doesn't support. And the main thing that we've done in terms of implementing features is we've added support for Play Movies in YouTube to play dash streams, which is a type of adaptive streaming technology. So it's similar to other similar streaming technologies. It's nothing particularly new. It allows you to encode your video streams at multiple resolutions and bit rates. And then during playback, you can adapt the quality that you're delivering to the user by requesting small chunks from different streams. And depending on the network conditions, you can then vary the quality that you're actually requesting in order to give the best resolution without giving the user rebuffers. So in terms of why you should want to do this, we've been doing this on newer devices for a while now in Play Movies, and we've been seeing some pretty good results. So here are a few. So compared with the old way of doing things using Media Player, we find that with Exoplayer dash playbacks, we can shave 65% off startup latency, so the initial buffering spinner before the video starts playing. We're able to reduce rebuffering rates significantly. So this is the number of playbacks, so the fraction of playbacks that the user will see a rebuffer interrupting their playback at some point. We've reduced that by 40%. And we've done all this while simultaneously giving the user higher quality content. So the video resolution in terms of height is improved by about 11% on average. So these are really great results. We're really happy about what we're doing and how we're improving the experience. And we really think that people should investigate this kind of approach as well themselves. But Exoplayer, our application-level media player, it took some time to build. It's about 16,000 lines of code. And the code is relatively complex. So building on top of these low-level APIs is, it can be a bit of a challenge just by their nature. And for that reason, we're giving you Exoplayer. We're open sourcing it. It's on GitHub already. Go and check it out. And this is pretty much the exact same core player technology that we're using in our Play Movies and YouTube applications. Thank you. So it supports Dash, although we're still working on widening the range of manifests that we support. But pretty much everything is there, and we're continuing to work on improving coverage there. It also supports smooth streaming, which is a similar adaptive technology. And we've deliberately designed it to be extensible. Obviously, you can just take the source code and change it, but equally, we've made it easy to inject things into the library. So you can do things like inject your own custom network stack if you want to, inject a persistent cache, and really it's just a much more powerful model for development. So that's what we've been doing in YouTube and Play Movies. Before I finish, I just want to say that we've learned quite a lot from developing this new media player ourselves. And we've been feeding what we've learned back into making our low-level APIs in the Android framework itself even better than they are already. So this started with KitKat. We realized it was quite hard to achieve very accurate audio-video sync. You could get pretty close, but there was some unknown latency in the audio track that there was no way to query. So we fixed that back in KitKat. We added a new getTimestamp API that lets you figure this out. And for devices running older versions of the Android operating system, Exoplayer also has a workaround which fixes the audio-video sync problem. There was also it's just a little niggle, but it's pretty annoying if you're a developer. Audio tracks write methods required you to give it a byte array, but actually when you decode audio using a media codec API, you actually get a byte buffer. So you had to do this pointless copy just to get data from one place to another. Our developer preview fixes that. We've added a write method that takes a byte buffer. And whilst we were at it, we also added a non-blocking variant in order to do non-blocking writes. And finally, but probably most importantly, is the problem of smooth video playback. So until now, you've had to time your calls to media codec release output buffer yourself, and you have to evenly space these so that the actual frames are dispatched in an even manner. And if you're running the old VM for Android, so Dalvik, this could be a problem if your garbage collector came and paused your thread at the exact time you were supposed to release the frame. You could get pretty good. You had to be pretty careful about not generating too much garbage. If you went to the Art Tech talk earlier, you will know that things are much better and have largely made this issue go away. We've actually gone a bit further, and we've added a new method which allows you to release a frame ahead of time, specifying a short period in the future where you would actually like that frame to hit the screen. And we've seen that this really helps improve the smoothness of video playback by letting the really low-level parts of Android time the frame release, and we've been investing some effort there in order to make sure it does a really good job of that. So with that, I'd like to hand back to Lajos, who's going to tell you some more about building experiences on the Android media APIs. Thank you.
All right. Thanks, Ali. So let's look at another example. We saw how Android can help you accomplish the real-time demands of video playback. But Android's low-level media APIs are also perfect for media processing. So that was Auto Awesome Movie from Google+. And it is a great example of how to use the low-level media APIs to create content. You can use these interfaces as building blocks, and they beautifully integrate with GL textures and shaders. For example, you can output decoded video onto a texture, even multiple videos, and then you can blend them together using a GL shader. And then you can capture the video from the resulting texture and encode it. So that's video editing. Or you can apply filters to the audio or video buffers to extract the information from them. For example, you can use the GLES shader to detect scene changes or changes in color balance. So then the question is, what can you do with these low-level building blocks? So I assert that it really depends on you. What can you do? So consider all the connectivity and additional sensors that are on a mobile device. And there is something amazing waiting to be created. So let's look at another example that uses video, the camera, and connectivity to help you connect to the people you love, even when they are far away.
It's a chance that he has to interact with his children because he misses out on so many memories. He's making a memory by telling these stories and interacting with them. That's just phenomenal. You can't even begin to imagine.
So that was Hangout, which also uses the low-level media APIs to do real-time communication. So let's start from a basic camera preview. And then you can capture the surface, the camera preview buffers, and apply a GL shader, maybe add a little hat, and then compress it. You can also compress a different stream from the same source, maybe a different hat, or maybe a lower resolution content for lower bandwidth. Then you send the packets across the network, and then on the receiver side, you use the adaptive playback features to seamlessly switch between the different streams. So this is basically the basic operation of Hangouts. So we are adding a couple of new features that will be fully exposed in the next release, such as dynamic encoder bitrate control and temporal layering. In temporal layering, the individual video frames are divided into layers. So the idea is that you should be able to decode all the frames in a layer without any frames in a higher layer. So this allows more radical bitrate control because you can discard, not even transmit, whole sets of buffers. For example, when you use 3 layers, layer 0 contains every 4th frame, so it's at a quarter frame rate. Layer 1 also contains every 4th frame, but together with layer 0, now the video is half rate. And then layer 2 contains the remaining frames, but here notice that each frame is droppable. So another thing that people like to do is share stuff. So if you're an Android mobile user with its tiny screen, and then you come across a large, beautiful display, you would want to take advantage of it, wouldn't you? So Android, by default, mirrors your activity onto external displays. And that works fine. But why not enhance your application by providing a differentiated, specific content on the second screen? So there are 2 sample apps. You can use Media Router and Display Manager to detect the additional display, and then you create a presentation to actually show the specific content on it. So there are 2 sample apps in the Android SDK that demonstrate you how to do this. Additionally, you can take advantage of nearby Google Cast devices, such as Chromecast or an Android TV device, and fling content onto them. So you use the Google Cast SDK for that, and it's supported for all Android 2.3 or later devices. Or after KitKat MR1, you can also present or mirror onto these devices. And now the icing on the cake. We have not forgotten about you, native developers, if you're in the room. So the low-level media APIs are now available in the NDK. And these C APIs mimic the Java ones. And you can use them on 32-bit or 64-bit binaries. And hopefully you visited the NDK booth already. But if not, check it out. There's still some specific content going on there. So I want you to think about how you can take advantage of these Android media building blocks. And where would media or video add to the delight of your users? And what is unique about the mobile experience that you could take advantage of to create that extra magic for your application? For a more in-depth coverage of our media APIs or of Exoplayer, check out our I/O Bytes. Maybe you already have seen them. And check out Exoplayer source. Now, Eddy will tell you about what's new in the camera framework.
Thanks, Lajos. So I'm Eddy Talvala. I'm the tech lead for Android's camera framework, and I'm here on behalf of my team to talk about what we've been doing for the last few years in Android camera. Cameras are great, right? You can use them to do all sorts of things. You can use them to record your memories. You can use them to share experiences you've had. You can use them to document the world. And if you're actually good at photography, which I'd like to be one day, you can actually create art like this. And the mobile devices have been getting better and better every year in terms of their cameras. The hardware is getting better. They're getting faster. And really, I think mobile devices can become better cameras than anything else out there, because they have so much more than just the camera. They have a lot of additional sensors. They have a whole lot of computing power, both the CPU and the GPU. They're connected to the network, so they know, so they can connect to the world and know about the context of where you are, what you've been doing, and connect to additional resources in the cloud. But right now, if you want to build an advanced camera API, it turns out the current camera APIs on Android really are holding us back. Advanced camera applications want more control of capture, more control of post-processing, and they want to do everything really fast. And right now, the Android camera API has limited capture controls, has very hardwired operating modes. You're either taking a picture or recording a video, or you can't do both. Very minimal feedback on what's actually going on in the whole camera system. And they are either very slow at high resolution, or if you want to go fast, you're limited to video rates. And they're completely unsynchronized. So it's pretty much a point-and-shoot camera. If you could just press the buttons by software is what the API is. So what I'm going to talk about today is our new camera API, which we built totally from the ground up to address these challenging new camera applications. It has a pipeline model, and it allows you to get full manual control of capture and post-processing. The pipeline model is fully synchronized, and you get feedback for every capture you take. And the data coming out of this, you can have multiple image streams coming out at full resolution, full frame rate, and it's all synchronized. So with the old API, if you want a full resolution 8 megapixel picture from your Nexus 5, this is what you get, 1 to 3 frames per second at 8 megapixels. With the exact same hardware on the Elb developer preview in our new API, you can do this. 30 frames per second, 8 megapixels, uncompressed YUV. Or even this, again, 30 frames per second, variable exposure time, full resolution. So what are we doing differently? What are we doing to enable this? Because it turns out that if you went back in time, the Galaxy Nexus could actually, at the low levels, capture 30 frames a second at 5 megapixels. It's maximum resolution. But this wasn't available in the API. So how come? So this is a very rough diagram of a real camera. There's a sensor, there's an image processor, and both of them have multiple stages that the image goes through. And of course, each of these stages has some settings, like the exposure time or the gamma curve or whatever. So I've marked the settings for each stage here with the little yellow S. When you're streaming data through for video or for high resolution, high rate capture, each of these pipelines is busy processing a different image. So here you can see image number 1 is finished processing, has been sent to the application, has gotten all the yellow settings applied. So with the old API, if you now change the parameters using the set parameters call, you do a global change. All the parameters change at once to the red parameters. And then if you look at what happens to the images flowing through the pipeline, some of them have already been processed through the yellow stages, and now they'll get red settings instead. So if you look at the output, the settings are inconsistent. Your first image is all yellow settings, the last image is all red, but everything in between is inconsistent, and you don't actually know if you have the exposure you wanted or the gamma curve you wanted. You have some mix. And of course, since every Android device potentially has a different set of pipeline stages, you really have no idea how long it'll take for any given setting to propagate. So if you want to do something really fast, you want to take a burst of images, it's very difficult to do because you don't really know when it'll happen and when you'll be done. So you could just slow down, and this is what usually happens when you take high-resolution pictures. So you just send one image through at a time. So settings are consistent, but you're now going 1/6 the speed as before. So this isn't very suitable for advanced applications as well. So instead, what we do now is that we look at the problem differently. each of the images that go through the system have the settings attached to them. So they flow through the pipe. The settings flow through the pipeline with the images instead of being these global things. So instead of having a black box that sends you data, you send in requests for images, and they get filled along as they flow through the pipeline. So here I have some yellow, blue, and red settings, and as they flow through the system, the settings go along with image buffers, and everything is consistent at consistent settings and high frame rate. And there aren't any modes here. You know, the system is simply a streaming, flowing API. You provide a request and outcome data that's synchronized to what you want. So let's take a quick look at the building blocks of the API that implements this pipeline architecture. To start off with, you just get a camera manager from the get system service call. The camera manager lets you enumerate camera devices, query their characteristics, like which way they're pointing, and then you can open them. So you get the information first, and then you decide it's the camera you want, you open it. The camera device lets you do two important things. First, it lets you create an individual capture session. You take a set of outputs that you want to target for this session and use it to create a capture session. And the outputs are simple Android surfaces. And then you can create capture requests. Each capture request, again, defines all the settings for a single image that's going to come out of the system. And then you start sending them the session. Session captures them asynchronously, and when it's done, it sends you back the metadata about the result. So the characteristics include things like the available manual exposure times, the resolutions and formats supported by this device, possible available autofocus modes, and the general capability flags of this device. The requests are all of the settings for a single capture. Here we're asking for 1 millisecond exposure time, color correction gains for post-processing, and continuous autofocus mode. And the requests also include which of the targets you configured for this session you actually want to use for this request. So for example, if you configured a session with a preview output and a high-resolution JPEG output, you might want some of your requests to touch target preview for steady viewfinder, and some of them that are user-triggered provide the JPEG data. So any subset of the configured services can be used in each request. And then on the output, you get the result. It contains timestamps, the state of devices like the flash. Here, the flash is fired. The autofocus is successfully locked, and it says there's a face in this particular image. And you know that it was exactly capture request, which capture request you sent in that was captured that has these statistics. So you can correlate this to image data and analyze it and know exactly what you got. So putting this all together, you start out with a set of outputs you care about. Here, some examples are surface view, the render script allocation, an image reader for JPEG, a media codec for video encoding or surface text to send to OpenGL. You get services from them. You create a capture session. And creating the session also defines your maximum frame rate. You look at the surfaces you've provided. It looks at the resolutions you want. And the maximum resolution defines how fast you can actually run this system. On the Nexus 5, we can run at 30 frames per second for 8 megapixel maximum output. But this may vary per device. And then once you've configured the session, you start creating capture requests and sending them. So everything is asynchronous. The requests go into a queue, get processed by the hardware in a pipeline. As the requests are processed, filled buffers are sent to your outputs with timestamps. And then results with timestamps are sent to the queue once the captures are complete. And this is the entire flow of the API. There aren't any other modes. There's no video mode. There's no still capture mode. You simply decide what requests you want. You send them in at the rate you want, and they come out when they're done at high rate. Of course, you can have as many of them in progress in the queue as you'd like. So I already talked about the different outputs, different destinations. You can get output in uncompressed YUV, compressed JPEG, or raw sensor data. And there's a whole lot of controls, and I'm not going to talk about all of them. You can control, there's a bunch of manual controls, and there's still a bunch of controls for the automatics, auto exposure, autofocus, and auto white balance. We have a large number of camera characteristics fields to read, all the settings, possible ranges for manual control, a lot of information about the sensor color spaces for raw sensor processing, and information about the hardware, the lens, and capabilities. And on the results side, we have information about the state of all the automatic algorithms if you're running them, and the state of the hardware, like if the flash fired and so on. We also provide some statistics like the neutral color point of the image, whether their face is, what the lens shading compensation map is. And we'll have a number of Android Dev Bytes videos about this. The first one should be going up soon on getting the very basics going. One important note that for the L preview this only works on the Nexus 5. The Nexus 7 or the emulator images don't run the new API. If you try, it'll crash in some horrible way. So that's a very brief tour of what the API is. The question is, what can you actually do with it? So our first serious shipping application is Hdr Plus on the Nexus 5. It's a Nexus 5's high dynamic range and low light mode. It was shipped using a pre-release version of our API in Android KitKat. So here's a sample image, a very hard problem. This is a dimly lit party, and this is a picture from Nexus 5 standard picture capture, cropped a bit. So it's very dark, so the denoising algorithms have to do a lot of work, and the picture as a result is very blurry and still kind of splotchy. So let's try HDR Plus. HDR Plus in 0.9 seconds captures 115 megabytes of data, analyzes the scene, and produces an output result that's on the right. As you can see, it's a lot sharper. It's a lot less noisy, and the dynamic range is actually improved. You can see the television in the background. If I zoom up close to the eye here, you can see on the left that there's barely any detail in the regular capture, where there's quite a bit of detail in the HDR Plus, and you can see the improved dynamic range. So this has been shipping. This is, uses the advanced capabilities of the API for manual capture and high-rate bursts. Another possibility you could do with the API is taking a stack of images with a bunch of different depths very quickly. So here, we move the Nexus 5 lens from far to near focus in about 0.8 seconds, capturing a set of 8 megapixel images as we go. You can now take this burst of images and analyze it for perhaps make an image that's in focus everywhere or create some sort of depth map. There's a number of applications. We're also enabling support for Adobe Dng Raw formats in the Android frameworks. So we will provide supported devices, including the Nexus 5. They will provide raw sensor data that can either be analyzed by the app or saved into a DNG file that can then be opened in professional post-processing applications like Lightroom, Aperture, or you can even upload to Google Photos, and they'll actually happily process your DNGs. And finally, I'm going to try a demo application of another interesting application. Let's see if this works. C is for camera. All right, so Rachad is going to be a model here. Stand right about there. So, all right. So as you can see here, this is a regular viewfinder on the Nexus 5. You can see Rachad just fine, but the audience is a little dark. So we have, I said we have manual exposure control, so let's see if we can do better. We switch to manual exposure. And the default exposure is a little bright on Rachad and still too dark on the audience. And to make this demo more interesting, this is not actually just manual exposure. This is actually a split-screen manual exposure. So I'm going to brighten up the audience a bit, and we get some really bad glare from the lights there, unfortunately. But you can see that on the right, I can see Rachad just fine. On the left, I can see the audience. If I pan over, the audience is black. If I pan the other way, Rachad is a little overexposed. So now I can see both sides, but I like to see it at the same time, of course. So let's use render script, and we have direct, efficient data processing path into render script, and blend this into a single high dynamic range viewfinder. So now you can see both Rachad on the right and the audience on the left, and the viewfinder is still rather smooth. It'll actually be a little smoother. Notice that on the right, I'm getting feedback about the exposure time. And the exposure time had actually gotten long enough that we were starting to drop the frame rate. So let me drop it back down to demonstrate this is actually quite smooth. And you can compare regular viewfinder. Rachad is so dark, the audience is completely gone. Split screen, and then the blend where you can see everything. And this all runs at 30 frames per second. And if you want to know what the secret is, how do we actually do a split screen? We don't actually have a fancy sensor. We're actually just alternating exposures every other frame in a continuous burst. So the sensor is not, every other frame is long, every other frame is short, and we simply blend the last two images we get out. So this is the kind of thing you can do when you're not limited to modes like burst. This is just, the API has one mode of operation, and it can do burst, it can do streaming bursts, it can do single images, whatever you want. All right, thank you, Rachad. So in summary, we made a new camera API for Android. We think it's pretty awesome. We really hope to get a lot of feedback during the L preview to help us guide what to do next and to get feedback on bugs, because there are still some rough edges we know about. So please take it for a spin on the Nexus 5. Let us know what you think. And I'd like to get actually Rachad back to wrap up. Thank you very much.
Hello, thank you very much. I hope you enjoyed the session. We'll all be available in the corner. If you have additional questions, we'll be happy to answer them. Thank you.